That the effect of the finite gain on frequency. So, or the dependence of the finite gain on frequency. So we finished the effect of offset voltage and bias currents on the op-amp output, and we saw ways to treat or to deal with bias currents and offset voltages. With the offset voltage, we saw that fine. There's you can probably it's going to be very difficult to eliminate it completely because of the matching of resistors. But in the worst case, you are passing through a portion of the offset voltage. Not even the full offset, you're portioning a portion of the offset voltage is going through. So we're not amplifying the offset voltage. So that's great. Otherwise, without trying to do something about it, we were passing the offset voltage magnified through the amplifier, which was a problem. Same thing with the bias current. With the bias current, we initially were passing the full bias current, full bias current through the op-amp. So we were passing the full bias current multiplied by even the gain through the op-amp, which was a problem because it was a problem for two reasons. We were passing through the bias current as well as having the R2, a limit, a constraint on R2 that is contradictory, right? The constraint on R2 was try to make R2 small so that the bias current doesn't pass through with the gain. At the same time, R2 small is conflicting with us trying to create a larger gain for the amplifier. So we said, okay, this doesn't work. So we added a resistor R3, and we found two ways to design R3 based on the fact that, based on the situation whether the inverting amplifier is capacitor coupled or not, right? So if it was not capacitor coupled, we designed R3 to equal R1, R2 over R1 plus R2. If it was a capacitor coupled amplifier, we designed R3 to equal R2. These are the two cases we studied last time. Now, today we'll study the effect. So this is the effect of V offset and I offset, the operation of the inverting amplifier. So this is just summarizing what we discussed, the effect of offset current and offset voltage and bias current. So now we will say the effect of what? The finite gain. So we initially designed or derived or looked at the op-amp, inverting and non-inverting amplifier circuits, right? And we assumed that the gain was infinite. That was the original assumption. And then there was one section where we derived the gain of an inverting and non-inverting amplifiers for a finite value of A, right? So I did one in class, and you did one as a bonus at home. So we did that. However, it turns out that the idea of finite gain is not just, the constraint on gain is not limited only to its magnitude. Remember, initially we looked at op-amps, and we said that two of the main characteristics of op-amps are that the DC gain is infinite, and the bandwidth is also infinite. Meaning, if I plot the frequency response of an op-amp, its magnitude of A over frequency. This is very high for any frequency, right? This magnitude of A is very high for any frequency. So A is very large. So if I plot its magnitude in dB, it's a very large number over all frequency spectrum, over the whole frequency spectrum, right? That's what we initially said about the op-amp. Then we said, okay, this A is not really infinite, it's a value, some value X. And we started playing with that. And we said, okay, this is fine, it still is okay, and we derived the transfer function equation for cases where A is a finite value, and we saw that what that does is instead of let's say for the non-inverting amplifier, as soon as we had feedback, we saw that what? We saw that if the voltage here was 0, that the voltage difference between these two was not 0, even with feedback, right? We had this was equal to minus V output over A, right? Let's say, because again, for the non-inverting amplifier, the output is equal to V2 minus V1 multiplied by A. That's equal to V output. We said if V output is a finite value, then V2 minus V1 is equal to V0 over A, right? If this is not infinite, then this is not 0, if A is not infinite, if A is not infinite, then V naught over A is not 0 anymore. If it was 0, then V2 is equal to V1. Then the difference between these is 0. Then we have that virtual short circuit issue that short circuit characteristic that we talked about. But if V naught over A is a finite number, then V2 minus V1 is equal to V naught over A. For the non-inverting amplifier, V2 happens to be 0 because I'm tying it to ground. So V2 is 0. If V2 is 0, then minus V1 equals V naught over A. So V1 is equal to minus V naught over A. That's why the voltage here, when we were deriving that relationship, was minus V naught over A. It was not 0 because of this. Right? So that's the effect of the finite bandwidth. Finite gain, right? Finite gain means A does not equal infinity. A is a value A. Right? So that was the effect then. But we still ignored the fact that it has a finite bandwidth. So this we dealt with, and we put something realistic. But we still kept this ideal. We said that the bandwidth is infinite, meaning this gain A is finite, and it's equal to 1,000, for example, and it's equal to 1,000 for any frequency. That's the other problem that we are assuming is not gonna be limited by physical design. It happens to be limited by physics, right? So A will happen to be limited by physics. So we will find that it's gonna be looking like a low pass filter. So it will be a high gain for low frequencies, and it will start to attenuate at high frequencies. Okay, and that is called, and this attenuation is something that it comes by construction from the device. From the op-amp circuit inside. Again, we don't deal with the op-amp circuit in this chapter. We do it in chapter 12. But from the design of the op-amp inside, this happens to be the case. So in order for us to be able to make this a more deterministic issue, people design op-amps with proper internal compensation. So internal compensation means what? Means that they put a capacitor in parallel. Remember in chapter 1, the problem that we had some amplifier chain, R coming here, R coming here, and then we had some, C here, and then our, dependent source, blah, blah, blah. We had something like that, for example, right? This capacitor here, what did it do? It's called internal compensation. It made this input look like a low-pass filter, right? So it makes the input look like a low-pass filter that I can control. And that's called internal compensation of the op-amp. So you are forcing the internal characteristics of the op-amp to have a certain low-pass filter characteristic so that you can deal with it. You know that, okay, so for example, for the 741, they tell you that the gain starts to drop at 10 hertz for the 741 amplifier. For the 741 amplifier, it starts to drop at 10 hertz, and it drops at minus 20 dB per decade. Minus 20, as soon as you hear minus 20 dB per decade, it means that it's a single time constant circuit. Right? So that's what's happening, that's what you're talking about here. So all of this means that, instead of just assuming a finite value for A, now I have to assume A has a finite value that is also frequency dependent. And it looks like a low pass filter. So if it looks like a low pass filter, then, and what is its DC gain? If it looks like a low-pass filter, what is its DC gain? The DC gain is the value of A, which is at low frequency, right? So instead of K, what's the equation for the low-pass filter? K over S 1 plus S over omega naught, right? This was our equation for the low-pass filter. Right, so I'm telling you that the physics or the internal design of the op-amp is forcing the gain of the op-amp to look or behave like a low-pass filter. So you can not just finite gain A, it's also going to look and behave like a low-pass filter, meaning it will look like its transfer function or the magnitude of A will depend on frequency in this fashion. Right? This will have a break frequency and it will have a DC gain. This DC gain is equal to A, and this is what K was here, right? So this A is which means that my transfer function for the op-amp will look like what? A over 1 plus S over omega naught, where omega naught is the break frequency that depends on the internal compensation that we talked about. Okay? So I have S over A over 1 plus S over omega naught for the filter itself. And because I don't want to mix it, yeah, they just keep it as omega naught. Yeah, they just keep it as omega B, break frequency. They call it omega B, right? So they call it omega B, right? So now instead of V output over A, which is equal to V2 minus V1, right? That was V2 minus V1 is equal to V output over A. Now I have to remove this A and put this. And then they made this, they call this A0 so that it's indication or that it is the DC value. So I take this and plug it in here. If I take this and plug it in here, how is this going to change the transfer function of the inverting amplifier? How is this going to change the transfer function of the non-inverting amplifier? That's the objective of this section. So it's like, deriving, basically what you did before was derive the transfer function of the inverting and non-inverting amplifiers for fixed A. Remove this A and plug in this. Right? If you remove the A and plug in this, let's see what happens. So this is the transfer function of A that I talked about. They also they give this point here at a term called FT. So FT, they call it the 0 dB gain, or the 0 dB frequency, or the unity gain bandwidth. So the unity gain bandwidth. What does unity gain bandwidth mean? It means it's the frequencies, the frequency bandwidth at which the gain of the amplifier is unity. So 20 log 0 is unity. So it's at which the magnitude of A crosses the 0. So how do you calculate that? If you go back to this the transfer function for a low pass filter, how do you calculate the frequency at which this will become 0? Does it happen at low frequency or high frequency? This 10 to the 6 versus the break frequency as 10 hertz. This is 100 hertz, 1000 hertz, 10,000 hertz. It's a very high frequency, right? But it happens at a high frequency. For the low pass filter, the place where the attenuation is becoming 0 dB is at high frequency, right? So they sort of say, okay, at S is a large number, what does this reduce to? Or at omega is a large number, what does this reduce to? If omega is a large number with respect to omega B, you can sort of neglect omega B, right? If omega is much greater than omega B, omega is much greater than omega B, you can neglect omega B, and you can sort of also neglect 1. Right? It's a large number with respect to 1, it's a large number. So this will reduce to A naught, omega B, omega is a large number, you keep that. Fine, you can keep omega B, they kept omega B here, but omega over omega B will be much larger than 1. Do we agree? If omega is very large, then omega over omega B is much larger than 1, so you can ignore 1. If you ignore 1, I can bring omega B to the numerator, and I'm left at the top with A naught omega B over J omega. Right? The magnitude of that is A naught omega B over omega. When does this frequency, omega, make the magnitude equal to 1? At omega equals A naught omega B. Right? If omega here is equal to A naught times omega B, right, then the top cancels with the bottom, and I'm left with 1. Right? If I plug this here, I'm left with a magnitude equal to 1. Correct? If the magnitude is equal to 1, 20 log 1 is equal to 0. So when will this transfer function cross 0? It will cross it at omega equals A naught omega B. Right? And they call that omega T, and they give it the name, the unity gain bandwidth. This is the magnitude in dP. It's equal to 0 dB, hence it's equal to unity gain. So this is called the unity gain bandwidth. Unity gain bandwidth. They call it WT, or the corresponding frequency is FT. Okay? Okay with this? So this is just okay. So this is a repetition of what I was saying. This is just the saying that the transfer function of the characteristic of the gain looks like a low pass filter. I removed S, put J omega, and then here we assume that if omega is large, what will happen? How can I rewrite it? We rewrote it as this. So we basically ignored the 1. We found the place where omega t crosses 0 by figuring out that this will happen at a naught equals a naught omega b, at omega t equals a naught omega b. So that's the sequence here. So we can now draw this characteristic. I know where this crossing is, right? If I know where this crossing is, from the data sheet, sometimes I will be given this. I will be given the gain a naught as well, right? You will be given the DC gain, right? But this looks like what? This looks like more like an integrator, actually, right? So with a small flat section here. Low pass. Okay. But what will turn out, so all of these are now characteristics of the op-amp. The characteristics of the op-amp are the low frequency gain. So that's a characteristic of the op-amp that you will find in the datasheet. Also, the break frequency of the op-amp you will find, as well as FT. It turns out that when you manufacture many op-amps, this is the most consistent property. This is the FT is the unity gain bandwidth is the most consistent property that you have. And if you know FT, you can sort of approximate everything else. If you know that this, and this is this is at 20 dB minus 20 dB per decade. So if you know FT, and you plot 20 dB per decade rise, you can sort of go all the way to here. So you can find the gain here, and if you know an approximate value for your 3 dB or the corner frequency, you will be able to calculate you estimate your DC gain, right? So DC gain and break frequencies are not as precise when you manufacture. This will turn out to be a very precise value when you manufacture. So this will be specified in the datasheet. So unity gain bandwidth should be specified. I did not check our 741 datasheet. Don't take my word for it if it's not there, but it should be there. But let's see. Electrical characteristics. Input resistance, large signal gain. Output addition, output of the common rejected supply, transit response, slew rate, supply current. It's not there. Large signal voltage. So we have a gain here, but we don't have FT. You can also, if you look here, you will find that none of these are given in frequency, right? So since none of these are in frequency, obviously they're not specifying that in this data sheet. So maybe let's skim through. Here, maybe. Bandwidth. Let's see, 2. Calculated from. So yeah, they're giving the bandwidth of the op-amp. So, but I'm not sure if this is referring to the bandwidth of until the break frequency or the bandwidth until the zero unity gain frequency, right? So this, I'm not sure what this is referring to, and they don't say here. But if we look at it's at 1.5 megahertz, right? So what does this probably tell us? Because they originally told us in the textbook that the 741 has a break frequency of about 10 hertz. So obviously this is not the 3 dB frequency bandwidth. This is what? Unity gain bandwidth, probably. Right? So this is FT. This is probably FT. Okay? Yes? No? Sheikh? Okay? No? So if you look at the textbook, let's see if they have the gain plots here in the datasheet. Maybe they will. They don't have the gain plots, frequency dependent gain plots. But in the datasheet or in the textbook, they tell us that these op-amps have a limited high gain bandwidth, or the limited high gain frequency or bandwidth, meaning the break frequency is very low. They're telling us that. And for the 741, they told us it's at 10 hertz, right? So I wanted to go and look at the datasheet and see if they're specifying any frequency. So I looked at all the parameters that they're specifying here. All of these are in what? Nothing in hertz, right? Nothing in hertz, nothing in hertz. This was the only thing in hertz. So this is bandwidth. They don't tell you if it's unity gain bandwidth or otherwise, but since it's for the 741 and it's equal to 1.5 megahertz typical value, and in the textbook here they tell us for the 741, they're telling us that for the 741 this is about 10 hertz, right? For the 741 this is about 10 hertz. The break frequency is about 10 hertz. So if the break frequency here is about 10 hertz, and that's what they're plotting, what is the unity gain bandwidth frequency? Here it's happening at what? 100,000, 10,000, 100,000, 1 megahertz. It complies with the datasheet. The datasheet says typical value is about 1.5. Minimum value is what? They said minimum value in the datasheet. This is something that you can use for your comparison work, for your bonus.
1 million?
Huh?
Is it 1 million?
Yeah, 1 million is 1 megahertz. So that's here they tell you that the typical value is 1.5 megahertz. The lowest value it can be is 0.4 megahertz. Right? So they're telling you this is ranging from minimum value of 0.4 megahertz. They don't tell you what the maximum value of it is, right? Since it's a manufacturing thing that you change with again, depending on how you manufacture the manufacturing tolerances, the temperature, blah blah blah, then the manufacturing process will affect this. Yeah, so they give you typical values, but this confirms the plot that they gave us in the textbook, right? The plot that they gave in the textbook. This is at 1 megahertz, and this is at 10 hertz, right? So they're telling us that these 2 points are there. So, but in the textbook, they also tell us that FT is what is typically specified in the datasheet. So here they do that next. So here, we know that the production spread in the value of FT between op amps of the same type is usually much smaller than that observed for A0 and FB. So you will have 3 main parameters: A0, FB, and FT. Your curve, your magnitude plot versus frequency is defined by A0, which is the DC gain, and the break frequency, which is FB, and your unity gain bandwidth, which is FT. These are the 3 things that define the op-amp's gain characteristic. So they're telling you that the most consistent parameter is FT. And you can sort of approximate the others by knowledge of FT. Because fine, we know that FB is low and A0 is high. So fine, at some point here, in this region here, we have an FB and we have an A. Is the value of gain going to be very precise? It's not going to be very precise. It's going to because the production spread is high for this value. So fine, assume it's ranging between here and here. Then FB ranges between here and here, for example. Right? So approximately you can do that. But what is really critical or defined very well based on the manufacturing process is FT. Okay, so that's what they're trying to say here. So how are they sort of justifying that? So they're saying, okay, that this is the magnitude for omega is greater than omega b, and this is the unity gain bandwidth, and then if you substitute with omega b is equal to omega t, right? If you substitute with omega t is equal to omega b here, substituting equation 244 gives. So if you take this, substitute it in here, you get the unity gain, right? That's what they're saying. But then what are they saying? What else? So this is the general format for the equation for the gain, right? If you write this in terms of frequency, this is omega t over omega. Since S is j omega, then this is omega t over omega, or ft over f. So you will find that gain will be equal to ft over f. So if you're given ft, you can sort of plot versus frequency. So if you're given ft, plug in different values for frequency, and you have an approximate value for gain. Right? That's what they're saying here. If you're given ft, plot that versus frequency, plug in different values for frequency, and then you will be, the result is gain. Right? That's what they're trying to say here. Anyway, so I think we spent a lot of time there, but the moral of the story is this ft. Right? That's the moral of the story. That it's a very well-defined parameter. And now we look at, this is the inverting amplifier's gain with a fixed or fixed value for A. So we will now remove this A and plug in the low-pass filter characteristic that we derived here. This low-pass filter characteristic, we will now plug it instead of this A that we had derived earlier for the inverting amplifier or the non-inverting amplifier. Right? Because now A is fixed in magnitude as well as not infinite in bandwidth. So I have to be this fixes A as a magnitude, but assumes the bandwidth is infinite. Now I will want to limit the bandwidth as well. So how do I do that? I plot A as a frequency dependent function that looks like a low pass filter by knowledge of ft. So if you do that, if you substitute with our A that we've derived as a low pass filter and do some simplifications, again I did not derive it, but I'm sure it's correct. If you do that, you will end up with this transfer function. This transfer function looks like what? Like a low pass filter. It looks like a low pass filter with a break frequency of omega t over 1 plus R2 over R1. This is your 3 dB frequency. Okay, so your 3 dB frequency is omega t over 1 plus R. So this is S over omega naught. Remember, my low pass filter looks like
1 plus S over omega naught.
exactly. So it's K minus K over 1 plus S over omega naught.
So I don't think it's minus K.
For
K is
the
K is
inverting,
gain, so
for the
it's
inverting
not
amplifier.
minus, it will be minus minus.
No, this is the T of S for the inverting amplifier.
K is already negative after over 1. Negative in front of it. Positive.
whether it's negative or not مش هنختلف يعني for K. It's the gain. It's the gain, the DC gain of your, which is for the inverting amplifier minus R2 over R1. So you can call it K R2 over R1. Anyway, we will not argue over that. But the idea is we put it in the same format, meaning I have a gain here that is not dependent on frequency and 1 plus S over something. This S over something is omega naught, your break frequency at this point. So this has a break frequency of omega t over 1 plus R2 over R1. So what happens when omega t is what? Large? What happens for omega t is large?
The whole thing will be bigger.
This
The denominator is denominator.
is very large. So I can ignore this with respect to 1. Right? Since the denominator will be large, I can ignore this with respect to 1. It's going to be, since S over something very large is a small number, so I can ignore it with respect to 1. I'm left with my inverting amplifier gain. Right? And I know this is a good check because it's a way for me to go back and see what's happening here. And this also happens when S equals 0. Put S equals 0, this also goes away. Right? So it also confirms the fact that without frequency dependence, the gain of the inverting amplifier is minus R2 over R1. So without the frequency dependence of the gain, this is the inverting amplifier's output here. Okay. It happens to be very similar also for the non-inverting amplifier. So you derive the non-inverting amplifier gain for a fixed value of A. We do the same thing. We take our low-pass filter characteristic of A, which is A0 over 1 plus S over omega naught. We plug that into this equation, do simplifications, and we will end up with this format. This format is also a low-pass filter format, right? Gain over 1 plus S over omega naught. And omega naught here, or omega base, happens to be the same as this one. It happens to be the same for the inverting a non-inverting amplifier. Since I'm using the same op-amp, right? Since I'm using the same op-amp, and this op-amp has a low-pass filter characteristic, then it makes sense that they have the similar break frequency, right? Yes, no? Okay? No, today's sleepy day or what? Guys, we didn't do much, really. We had derived this before. All I'm saying is now remove A and put low pass filter. Put A naught. Put A naught over 1 plus S over omega naught. Omega naught happens to be something, happens to be in terms of omega t, because of the low pass filter characteristic that we had. So this was the low pass filter characteristic we have for the op-amp itself. It has a break frequency and it has a unity bandwidth frequency, FT. And we said that we can rewrite, we can estimate A0 and the break frequency using omega t somehow, right? If we assume that omega t is greater than omega, these assumptions that we had, we can sort of come up with, relationship between gain and FT. Right? That's why this omega t appears into this equation here. And do the simplifications, this is what we're going to get. We get with no dependence on frequency, this goes away, and I'm left with the gain of the non-inverting amplifier. If I assume that there is dependence on frequency, meaning I put this into the picture and do some simplifications and use the assumptions of omega t is greater than omega base for the op-amp, etc., I will end up with something that looks like this. If you want bonus and you want to derive it, go ahead and derive it. I'm happy. I did not derive it myself, but I don't have for a 0.5% bonus, if you want to derive this in detail, I'm happy to do that. You can go ahead and do that. Be my guest. Okay? It will convince you. I did not derive, right? I did not derive. I'm telling you that take this, plug it in here, and use the assumptions of that were given in the previous section, which were, the assumptions that led us to the magnitude of A being ft over f, or that A of s is now omega t over s only, instead of the full loop. This looks like what? An integrator. This looks like 1 over s. This looks like a 1 over s versus the original low-pass filter, full low-pass filter looks like this. This is the original low-pass filter. Right? You can take the original low-pass filter, plug it into the equation of gain for a finite value of A, and do the simplifications. But you also need to consider, I think, when you derive it, you need to consider the simplifications that they made here. What were the simplifications that they made here? The simplification that they made here is something that led us to the A of S, or A of j omega, equal to omega t over j omega. That's what it led to. If you do the substitutions, you should be able to get what they got. I did not derive it, but I'm sure there's nothing wrong with it. Okay? So any questions? 0.5. You derive them both. Okay? Both. Both, for inverting and non-inverting. Okay? So, at least, is the process clear? Is the process clear? Which simplifications they used? I'm sure that they used the simplifications in this previous section. I did not derive it myself. I'm happy to receive your derivations. We're finishing it, yes, we're going to finish it. So this is an example that takes this equation, and for the non-inverting amplifier, and this is the gain for the inverting amplifier, right? Including the effect of frequency of A, right? Now they're telling us, okay, plot the magnitude and phase of this. Fine, you can come up with the magnitude of this transfer function and the phase, and plug in different values for omega, and plug. So they're giving you, okay, here telling you to plot the magnitude and phase at, for A is equal to 1000, 100, 10, 1, minus 1, minus 10. So this is non-inverting, right? And this is for, all this non-inverting, and this is for inverting amplifier. So they want you to design an amplifier with ft is 1 megahertz, so you know omega t, and the 3 dB frequency of the closed loop amplifiers, gains being, so this is A0, so they're telling you, they're giving you ft and they're giving you A0, right? So remember, ft and A0 they're giving you. So from the approximation of A is equal to ft over f, then, and knowing 2, you can plot the third one. Right? So you can do that. So sketch the magnitude and frequency response for the amplifiers with closed loop gains of plus 10 and minus 10. So they want the closed loop gain of these amplifiers to be plus and minus 10. For the ones that are plus minus 10, they want you to sketch them. For the others, they just want you to calculate. So find the frequency of the closed loop amplifiers with nominal gains, so and so. So here, so they're giving you gains, and they want you to find the corresponding 3 dB frequency for a given FT. We know that FT over F is equal to the gain. That's the approximation from the amplifier. So you find the magnitude and phase of this, and you find the magnitude and phase of this, and you find, in that case, they want you to plot them for the plus 10 case and the minus 10 case. For a closed loop gains equal plus or minus 10, you want to plot them. What else? They want you to calculate them. So the closed loop gain for the gain of equal to 1,000 case. So this is the non-inverting amplifier with a gain of closed loop gains of 1,000. So this is the non-inverting amplifier. If you find its gain, equate that to 1,000, and that's this case, right? What is R2 over R1 in this case? It will happen to be 999. And then they're asking you to find what is the corresponding 3 dB frequency. The 3 dB frequency is from here, omega t over 1 plus R2 over R1. Okay? So what is that equal to? It happens to be 1 kilohertz for this gain. Same thing, go back to 1, you have a closed loop gain of 100. For a closed loop gain of 100, this is my transfer function. Find its magnitude. And then you equate that to 100. After you equate it to 100, what is R2 over R1? R2 over R1 will be 99 in this case. You do that, you take that, and then you plug in the equation for the 3 dB frequency and calculate the 3 dB frequency, right? They're just plugging into these equations. The nice thing about this is something new, something interesting comes up. If you look at the multiplication of closed loop gain and the 3 dB frequency, what do you notice? These are substitution numbers, nothing. This is just substitution. What happens? So when you're decreasing the gain, what happens to the break frequency? Increasing. Right? So when you're increasing the gain again, what happens to the break frequency? Decrease. Right? So it means what? It means that these op amps have an interesting characteristic, like that they operate with something called, they're guided or they're constrained by what is called the gained bandwidth product. So the gain of the closed loop gain of the op amp multiplied by the bandwidth is a fixed number, approximately a fixed number for the op amp. So this is one of the characteristics for the closed loop op amp operation. Right? So this is large, this is small. This is small, the bandwidth is large. It's just a characteristic. There's a compromise somewhere. It's just from the equations. The reason is the low-pass filter characteristic of the op amp that you're using. You have a low-pass filter characteristic. How is this capacitor? Which means that there's a capacitor in there in parallel, right? So this capacitor in there that's in parallel. If you want a large gain, remember the time constant is going to be what? Probably very large. I want to try to explain it, right? If the time constant is very, very large, what does this mean? It takes a lot of time to process a signal. Means what? Means that the signal that you can process will be limited to low frequencies, right? If you try to make sense out of it, right? You have a capacitor in there, and the capacitor will have some resistors in parallel. When you remember the trick that we did, short the voltage sources and look at the resistors in parallel with the capacitors. The resistor in parallel with the capacitor, if you have a very large gain, R2 over R1 is large. If R2 over R1 is large, then these resistors that are in parallel are going to probably be large. R2 is much larger than R1, right? So then you have a large time constant. Large time constant means more time to process the signal, because for voltages to rise and fall, it will take time. So if that's the case, that means that you're going to be limited to low frequency signals to pass through this amplifier. I'm just trying to explain the physics behind it. But, so, and that's what it's due to basically the capacitor in parallel.
So,
Yes.
there's something confusing me about what is the difference between closed loop and open loop. They always say it, but in the questions we never really.
No, closed loop means you have the amplifiers around it. You have the resistor circuits that are creating the inverting or non-inverting amplifier configuration around it. That's the closed loop gain. This is closed loop gain for the inverting non-inverting amplifier, and this is the closed loop gain for the inverting amplifier. They're telling you that this closed loop gain, closed loop amplifier with nominal gains of 1,000, sorry.
Okay.
They're telling you that this closed loop gain, make it equal to 1,000.
Okay, no.
If you make it equal to 1,000, what? And so this is the gain.
No, that's not my
At DC, put S equals 0, then 1 plus R2 over R1 is equal to 1,000, so you can be able to calculate R2 over R1.
Okay, but what is the open game now?
Open loop gain
Yeah.
is without the resistive circuits around it.
So is for the inverting amplifier negative R2 over R1.
That's A0. The open loop gain,
But is that open loop gain,
the open loop gain here, the open loop gain is A0.
which is negative R2 over R1?
No, the open loop gain is A0. How did it not appear here? How did it not appear here? It didn't appear here because of the simplification that we used here. That the magnitude of the open loop gain is Ft over, the magnitude of the gain is Ft over F. We were given Ft. So you plot versus F, you will be able to calculate the value of A at any frequency. So it disappeared by this fraction, by this simplification. So we should have seen A0 somewhere, right? We should have seen A0 somewhere, but it disappeared because it's part of Ft. If you know Ft,
I still don't get what's the difference between
Okay.
open loop and closed loop.
here, okay.
Like when he asks
Open loop
us
gain.
questions,
This
sometimes
is the op-amp, plus minus, right?
Yeah.
Like this. What is the output? V2, V1. What is the output here?
Yeah.
V output equal to A times V2 minus V1. This, in this case, is the open loop gain.
Because there's no resistors or anything.
Nothing around it. Yeah, nothing around it. This is the open loop gain. And it is undefined, right? It's not defined. Because we said it's infinity, right?
Yeah.
And then with the assumptions that we talked about today, we said that it is not really infinity, it's limited, okay? But from a manufacturing perspective, it's very difficult to define it as a value. So what is the best way to estimate it from a manufacturing, from a design perspective? The best way to estimate it is by looking at Ft. You take your point from Ft from the datasheet. It was 1.5 megahertz for the op-amp, the 741 from our datasheet. And then you go to your magnitude of A plot. This magnitude of A is going to look like what? They're telling us that the characteristic of A as a transfer function looks like
No pass.
a low-pass filter. So, which means that, and it's a single-time constant low-pass filter. That means it's going to decay at minus 20 dB per decade. So this is Ft, this is Ft over 10, this is Ft over 100,
Yeah.
blah, blah, blah. And then this is 0 dB, 20 dB, 40 dB, etc., 60 dB. And then I take this, I go every decade, I go 20. So I'm able to
Estimate A.
plot this, which is an approximation of the op-amp's transfer function, which they gave us as Ft over F.
Okay.
Right? What does this look like? Ft over F. This is a fixed number for any value of frequency. Exactly, it's like whatever. So it looks like this straight line.
When you log.
When you plot it, it looks like the straight line when you plot it on a log scale, right? So, and they're telling you that the A0 is a characteristic of the op-amp, but we don't know exactly what it is, and it's very manufacturing is not, you cannot tweak it. So it can, and they're also telling you that FB, the corner frequency of the low-pass filter, is very small. So for example, you can be here. And this can be the magnitude of A0, and this can be FB. Or you may be here. And this can be FB, and this can be your A0. Does it really matter? It doesn't really matter. I mean, fine. But they were both, these are close enough to each other And they were very well defined by knowledge of FT, which is given in the data sheet. That's what they're telling us.
And as soon as there are resistors, then we're finding the closed loop gain.
Yeah, as soon as you put resistors, you're finding the closed loop gain. So we took this closed loop gain of the amplifier by itself. This is not this is not really the closed loop gain of the this is now the open loop gain of the amplifier A, but depend with the frequency dependence in there. And then I built circuits around it. Whatever. Now, when you build circuits around it, it's the closed loop gain. I will take this equation for A of j omega here. This is a j of A of j omega, equal to what? Equal to ft over f. This is ft over f. I plugged it into what I know about the inverting and non-inverting amplifier gains with a fixed value of A. I plugged it in here. When I plugged it in here, I got something that looks like this. They're telling you, find the magnitude of this and the break frequency. The magnitude of this, you can find the magnitude. And the break frequency, you'll find the break frequency. Magnitude is easy because it's, put S equals 0. S equals 0, equate this to 1,000. You'll find R2 over R1. S equals to 0, equate this to 100. Find R2 over R1. And that's what they did here. Found R2 over R1 for various values. And then they also substituted in the break frequency. They calculated the break frequency. They're telling us that, look at this. When you multiply, or when you look at a high gain, you're looking at small bandwidth. Low gain, you're looking at high bandwidth. So they're telling you that the gain bandwidth product for any op-amp circuit is a fixed value. Right? That's what they're telling you. So this is the reference to that. Okay, the last few things I want to discuss about the chapter is we talked about if you put a signal into the op-amp, after with a closed loop, you put your closed loop. If your voltage on the supply voltage is plus minus 5 volts, and your gain is 10, can you put a signal of 1 volt at the input? If your closed loop gain is 10, assuming your closed loop gain, A closed loop equals 10, and your supply voltage VCC and VEE are plus minus 5 volts, right? That means that my signal can only swing between minus 5 and 5. If I put a signal of 1 volt, that's my input, 1 volt sine wave. This is 2 volt peak to peak or 1 volt peak, okay? Then if I multiply it by the gain, what am I going to get? Multiply by the gain, what do you get? 10 volts, right? Assuming this gain is, infinite bandwidth, right? Then you will get a signal that has a peak value of 10. Your supply voltage is 5. Can you produce a signal greater than your supply voltage?
It's going to be cut.
You cannot. It will be clipped, right? It will be clipped. So this is a distortion of the signal, right? So you distorted the signal because you tried to operate outside your supply voltage rails. And that's why, remember all of the discussion about offset voltage and bias current. The problem with the circuits without taking care of these issues, bias current and offset voltage, was what? Was that this offset voltage and bias current were passing through my circuits and being amplified. They are being amplified. What does that mean? They're eating from my ability to produce a larger signal at the output, larger useful signal at the output, right? So let's say I have some DC content here to this signal, that offset voltage. What does that mean? That means that I'm going to be amplifying my offset. Let's say I have 1 volt offset. So 1 volt input offset voltage. What does that mean? If I amplify it by 10, that means my offset voltage is 10 volts. So just my offset voltage will ruin anything. I mean, I will not get any signal. My op-amp will saturate. Not even clip my signal. Right? If my V offset is 1 volt and I'm amplifying it by 10. So what is the output going to be? Saturated at 5. All saturated. So I will lose all the signal content. And that's why I don't want to amplify my offset voltage. And I don't want to amplify the effect of my bias current. I want to I have a 1 volt Offset voltage, okay, I'm not able to deal with. The best I can do is let it pass through as an offset voltage. Okay, so I will have 1 volt here that I lost. But I still see my signal. I cannot amplify my signal as much as I wanted to because I'm losing some because of the offset voltage, right? The offset voltage is there, it passed through, but it's not being amplified. But at least it's passing through as an offset voltage without magnification. But my signal is being magnified. So instead of 1 volt, now I can multiply the signal by maybe 3. So now I have, or 4. 4 volt signal peak, and then 1 volt offset. I'm still within my 5 volt range, right? So I can multiply, or I can create a circuit with a closed loop gain of 4, have my input signal pass through, be multiplied by 4, so plus minus 4, shifted with an offset voltage of 1. That means I'm at the power supply rail voltage. I still did not lose any content. Yes? Okay? So that's called output voltage saturation. When you clip, you saturate the signal. There's another way to saturate the signal. Okay, so we kept talking about, these op amps are nice devices. Ideally, what does the output circuit look like? A dependent source with gain of A and A V input, where V input is, this is our input, this is minus, plus, minus V input, right? That's what we said. This is the ideal op amp approximation. This is an ideal dependent source that will just look at the value of VA and multiply it by a very large number. Meaning what? Meaning it can produce very high voltage here, theoretically speaking. It's fine. Then we said it's limited by the supply voltage rail. It's limited by it cannot exceed that. Okay, that means A is a specific magnitude. But what if I put a short circuit here? How much current can flow through here? Why? Infinity. Theoretically infinite. Right? But this is all theoretical. There's no such thing as allowing infinite current to flow through a device that's this small. Right? Everything has, if current's going to flow, it means it's going to flow through something that has some resistivity, which means there's some loss, which means there's some heat generated. So every op amp will have a rated current. So for the 741, the rated current is 20 milliamps. If you try to exceed the rated current capacity of the device, of course you will fry it, but before frying it, because you always have a margin, but before frying it, what's going to happen is it's also going to clip the output. So even though you may not be magnifying the output by gain of 10 and moving from 1 volt to 10 volt, it's not being clipped because of the output voltage being greater than the supply voltage. It's being distorted or clipped in that case because of the output current exceeding the rated current. That's another reason that you can clip it. How does it look? It will look like something. It's not a basic clipping. It will distort the signal. They don't show what it looks like here. I think it would be nice to try that experimentally. They give you an example here on that. They give you a system where you have an op amp, and they tell you. And by the way, when we talk about current, we are referring to both the current in the load and the current in the feedback path. Right. So if I'm telling you that the rated current of the 741 device is 20 milliamps, 20 milliamps, you have to calculate 20 milliamps. You have to calculate the current flowing in this load here, because this is being supplied by I output, right? This I output is supplying both the current here and the current here. It's supplied by I output. So you have to add this current and add this current and make sure that they are both less than the rated current of the device. Otherwise, you will clip. Right? So they give you some examples that are very straightforward, so I will not go through them. They just calculate, okay, they calculate the current. We derived the currents in these circuits, right? There's inverting amplifier, non-inverting amplifier. We know how to derive the values of the currents. So just derive the value of the current and calculate current here. You know the output voltage divided by the resistor, calculate the current here. Make sure that they're both less than the value of the rated current of the device. If that's the case, it will not clip due to current. Is it going to clip due to voltage? That's their question. Is it going to clip due to current? No. Then you check, is it going to clip due to voltage? Yes or no, right? And then the last question they ask you, what is the small or the lowest value of RL that you can put in there so that you don't clip? Basically, they're telling you what is the maximum value of current that you can push without exceeding your 20 milliamps. That's what they're saying. Okay? So look at this example. It's pretty straightforward here. The last topic. We're done with the chapter. So the last topic. If you remember this, this is a physical system. The op-amp is a physical system. So as a physical system, you cannot just put a square wave with infinite rise time and infinite fall time and expect that the output will, rise. So if this is a comparator, if you're just running it as a comparator, what do you expect to see? When when V2 is greater than V1, you expect to see an output rise. And when V1 is greater than V2, you expect to see the output fall. Right? That's the general case for V2 if it's running it as a comparator. This rise and fall takes time, right? This comparison is happening inside the op-amp. The gain of the op-amp is A V2 minus V1. Where did we come up with that? It's because of the way that the circuit inside it was designed. The circuit inside the op-amp has a time constraint. Everything has a time constraint. So, when we look at BJTs and MOSFET, we will see that a BJT or a MOSFET has a turn-on time. It takes time for, you tell the device to turn on. It will take time for it to turn on. You tell it to turn off. It will take time for it to turn off. Right? So, and this is independent of the characteristic of this low-pass filter that we're talking about. So there's something that's this limitation on rise times and fall times of signal is called slew rate. They describe it as slew rate. So slew rate is the slope of the signal that is of the input signal. So if you have an input signal, for example, so it's the slope of the output signal, but it's defined by the shape of the input signal. So let's look at this, for example. If you have a square wave like this, and you are being limited by the slew rate, what will that do? Because these are two cases. The slew rate will cause your signal to be distorted. It will take time for it to rise and then reach your, the required, final level.
It can't instantaneously.
It cannot instantaneously rise, right? But please note that this slew rate is different from the low-pass filter characteristic of your amplifier. So if your signal is slower than the slew rate, so if you're not putting a step waveform, you're putting a waveform that looks like this. It looks like this. You're putting a waveform that looks like this. And your slew rate is actually here. This is your limit on your slew rate. This is your limit on your speed of rise of signal. And that is typically given in microvolt per second. And you will see it here in the daily sheet for sure. Slew rate, microvolts per second here. Slew rate, right? Slew rate is here. It will be given in microvolt per second. So it will be always given in the data sheet. So this is one of the comparison points between op-amps here. So if your rise time of your signal is less than your slew rate, are you being limited by slew rate? No. This signal, this step waveform was rising infinitely fast at the input. So at the output, let's say if you have a unity voltage follower, unity gain amplifier, what do you expect to see? You expect to see what you have at the input. Is it going to rise infinitely fast? No, because of the slew rate. This op-amp has a slew rate. There's a maximum rise time of voltage per second. Right? So here your step waveform was limited because of the slew rate, and now it was distorted to look like this. How about if you have a signal at the input through a unity gain amplifier as well? There's a unity gain amplifier or a voltage follower that is not rising as fast as the slew rate. This is your slew rate limit, microvolt per second. Your signal is this. Is this as fast as your slew rate, rising as fast as your slew rate? No, it's not. So since it's not rising as fast as your slew rate, what will it be affected by? This will be affected by the low-pass filter of your op-amp characteristic. And the low-pass filter op-amp characteristic is more of an exponential function rise. That's what we derived last time. 1 over 1 plus e to the minus t over tau. It's an exponential rise due to the low-pass filter characteristic of your op-amp, versus the limit due to slew rate. Okay? Do you see the difference between them? Slew rate is something, and the low-pass filter characteristic of your op-amp is something else. They are different. Okay, so the signal can be the signal will be distorted due to slew rate. but it will be processed based on the frequency response due to the low pass filter characteristic of your op-amp. And this is the end of the nice chapter that we discussed. They're just saying you here that the slew rate is basically you look at it's basically a differentiation of your input signal. It's, and it's, yeah, no continuation. The slew rate will just distort your signal, right? That's what we need to do on slew rate. But you need to read this if there's a homework. Yeah. No, you should read this. You should read about it. It's one page. Come on, it's one page, and it just says if your signal frequency is greater than the frequency or the speed of rise of the signal of your greater than the limitation of the slew rate.
Yeah.
So you have a very high frequency signal, and that signal is also high in magnitude. What does that mean? So here, let me try to explain it quickly. Sorry, sir. If you have a very large signal, you have a sine wave here. That is right. That's a high frequency signal. Okay. This is another high frequency, same frequency signal. Okay. What's happening at the zero crossing? This is same frequency. You agree that signals here are same frequency? Same frequency. This is same frequency. Zero crossings are the same. So this is signal 1, this is signal 2. They have the same frequency. Right? But let's zoom in here. Because they have different amplitudes, what happens to the slew rate? Yeah. This one is rising much faster than 2. 1 is rising much faster than 2. So 1 would be limited by the slew rate. 2 would not be limited by the slew rate. So the way to define to do this is typically we would put the maximum we would put in the put the sine wave in the op-amp and put its magnitude at the maximum voltage of the plus almost of supply rails, plus minus 5 volts for example. You supply, put the input signal at plus minus 4.5 volts for example, right? And then keep increasing frequency. If you keep increasing frequency, at some point you'll be hit by the slew rate. You're at 1. You're doing this. You're putting 1. You're putting a very large magnitude signal equal to the maximum that you can put through the op-amp. Increase its frequency. At some point, you're going to be hit by the slew rate, and the signal will be distorted. Right? What happens if I decrease the magnitude of the signal? If you decrease the magnitude of the signal, you will not be hit by the slew rate anymore. You will go back to your sine wave.
Yeah.
Right?
So and then if you keep going, it's going
to and that's what's called. So the full power bandwidth is this full magnitude signal, and where it starts to be affected by the slew rate. That's the full power bandwidth.
So basically,
full power means maximum voltage out of the op-amp for the maximum frequency content.
Okay. So
right?
Basically, the slew rate is when the higher it is, the frequency is, the more distorted the signal would be, or the lower.
So the higher the frequency is,
the more distorted.
The more you may be affected by slew rate. You will be hit by slew rate. But it's also dependent on magnitude of the signal.
Okay.
If you for the same signal, as soon as you start being hit by the slew rate for the maximum value signal, start decreasing the magnitude. No, don't decrease frequency. Just decrease magnitude. If you decrease magnitude, then you become like this number 2 waveform. Number 2 waveform has a smaller rise time. This is number 1 waveform. This is number 2 waveform. 1, 2.
It's the same signal.
It's the same frequency.
Yeah.
Same frequency, but it has a different peak value, Vmax.
Okay. So basically, same phase.
Same phase, same everything.
Different magnitude.
Different magnitude.
That's
if you decrease the magnitude, they're telling you that if you decrease the magnitude, you're able to do what? You're able to increase this frequency at which you'll be affected by the slew rate. So decrease magnitude.
Yeah.
If you decrease magnitude, you can put a higher frequency signal through. Right? That's what this means.
Basically, this is a way to manipulate the signal so you can go underneath the
slew rate limit. So you have a constraint on slew rate.
Yeah.
Okay. If you have a constraint on slew rate, that's distorting your signal. What do? You have to decrease the gain.
Makes sense. Yeah.
Decrease the gain. And at maximum gain, that's called the full power bandwidth. It's the maximum amplifier gain that you can allow, and you see where this FM is, the F max is. That's going to be your full power bandwidth. Where does your full power bandwidth? It's maximum signal gain, and this frequency that you're going to define.
So let's just barely cover it next class.
No, that's it. I'm done. We're done with chapter 2 completely. That's it.